Good afternoon. I'm going to get started. My name is Tim White. I'm a research professor in geosciences and in the Earth Environmental Systems Institute. And it's my pleasure to introduce Elisa Alonso, who, if I'm honest, I just met today. But I did a little sleuthing online to learn about Elisa. She's got her bachelor's degree in metallurgical engineering from McGill and a PhD from MIT in material science and engineering. And the little bit of sleuthing that I did, some of the interesting things I found out about you is that you've got some interesting hands-on experience with lead zinc beneficiation, and I think even working with sheet metal and maybe some welding. Is that correct? Welding aluminum. She spent some time off in Taiwan learning Chinese, and all the things she's done with the federal government, I have to read to you because her titles are quite long. She is currently the assistant chief for the Mineral Intelligence Research Section and the acting deputy director at the National Mineral Information Center. And she is also the deputy program manager for the DARPA Open Price Exploration for National Security Program. And I'm looking forward to your presentation. I think it's going to be very different but a great addition to this series this semester. Thank you for being here.
Thank you so much, Tim, for that introduction. I almost didn't make it here, but when everything reopened last Wednesday, we got the paperwork done really quickly, so here I am. I'm really glad to be here. I've met some really amazing researchers and seen some awesome materials characterization lab equipment, so it was a really exciting day for me. Today I want to talk to you about how to increase transparency for critical minerals, commodity supply chains, and to think of the supply chain starting at the deposit all the way to the final end use, and to consider uncertainty and the opaqueness of these markets as we try to understand them. So I work as, right now I'm the acting deputy director for the National Minerals Information Center. We're about 100 and so people. We're really divided into 4 groups. One of our groups looks at trying to get as much data as possible from the US about its minerals, deposits, production. And so we send out surveys across to these industries and collect the data and put that data together into minerals industry surveys. One of our sections focuses on having specialists for each of the mineral commodities. So we have a gallium specialist, an aluminum specialist, copper specialists. Usually our specialists cover 3 to 4 mineral commodities. And they produce annual minerals yearbooks as well as a mineral commodity summary, which is something that's used actually quite a lot across government, especially now. We will usually bring a box of mineral commodity summary, printed copies over to Congress and other folks in government so that they have quick access to understanding different mineral commodities across the periodic table of elements. We also have a global minerals analysis section, and this is where our specialists focus on regions to understand these mineral commodities, right? So the supply chains of these mineral commodities is global. Just focusing on the US is not sufficient for understanding where these commodities are coming from, what their markets look like, what their end uses will be. And so we have these specialists with mostly specialty in foreign language skills, but also understanding of geology and sciences to be able to tie the two together and understand the international aspect of mineral commodity supply chains. And finally, my group is the Minerals Intelligence Research Section. We take all this data and try to analyze it and make really fun, fun research projects to illuminate supply chains. What we've done now from 2018, 2022, and this year is provide technical input to the federal government for the critical minerals list. That's the federal critical mineral list. And just last week, the final federal critical minerals list was published on the Federal Registry Notice. So this is sort of what NMIC does. And I've been there since 2020. And before that, I was working with USGS as a contractor, but through the National Defense Stockpile. And so, right, so that was where I got to see the USGS data be used for making decisions about stockpiling for our national defense. So what my group is doing in particular is really trying to build a suite of models and tools to track mineral commodity supply chains. And we think about this starting right from like, what do we understand about these deposits? How do we think about the whole periodic table, not just the base metals like copper, aluminum, but also the byproduct mineral commodities that come with them and the economics aspects. So not just the material flow that's tied to that, but also the economics that makes those mineral commodities tied to each other. We also think about this from an asset, mine, and facility level, not just at the country level. And then we look at trade and try to understand the global material flow analysis and where they're going in indirect trade and embedded trade. So like, what is the amount of gallium that you brought in when you imported your cell phone from another country, right? So that's the type of embedded trade that we try to track. And then we take this and understand what does this mean for the federal government and for our economy in terms of risks for supply? Like, what happens if there's a disruption? What does that cost us? And we also think about externalities. This is a project, right? So like rock to metal ratio. How much rock do you have to mine in order to get 1 kilogram of platinum, 1 kilogram of copper, et cetera? And then finally, we've started bringing in, and we've got some economists on our team to really build the economic analysis. So what's the price elasticity for these commodities? What's the supply elasticity? What does this mean when we look into the future for these commodities? And so that's one of the other tools that we're building. We support a whole government effort, and in particular, as Tim noted, I'm the Deputy Program Manager for the DARPA Open Price Exploration for National Security Program. What DARPA has tried to do is to take, right, so USGS has done this, but they're doing this at a bigger scale, to take these machine learning, AI tools that are being developed to apply these to mineral commodities, to have a better understanding, especially of the minor metals where there's not a lot of information, to get this kind of concept of what's the structural price? What does it take? How much does it cost to build a mine, to process a mineral commodity, to incentivize domestic producers to make these commodities? Let's look at it from a commodity by commodity perspective. And let's also let them know, like, what does the supply and demand look like going forward so that they have some future certainty, right? When they build these mines, they need to think about this, about, do I have a customer in 5 years? Because I'm building this mine for 15, 20 years. So this is the DARPA Open program, and we've been really going through the whole, through the critical minerals list to do this kind of analysis. And it's lots of fun. I think about it as sort of like doing comps, like when you're buying a house, like how do you compare these different commodities to each other and what kind of data can you glean from it? So why are we even talking about mineral commodities, right? So one of the things I want to bring us back to, and as a material scientist, I take this for granted, but really we can't take it for granted. Folks don't think about it that way, but mineral commodities enable faster, smarter, smaller technologies and support essential infrastructure, agriculture, manufacturing. You can't just replace neodymium with iron, right? You have to use the material properties that are inherent in these materials so that you get like gallium nitride that's smarter for your chip, a lighter material with aluminum lithium alloys, right, for your planes so that they can fly farther on the same tank of gas, higher yields with agricultural fertilizers like potash and phosphates, stronger materials, high strength low alloy steels using specific commodities like vanadium, niobium, molybdenum. Hotter, so super alloys, super important to get your rhenium, potentially your thermal barrier coatings with yttrium, right, into those products in order to be able to run at high temperatures. And then sharper, right? So you want that imaging to be really sharp for your magnetic resonance imaging, and you're going to use special magnets for that. And those are all enabled by mineral commodities and the properties that they provide. But the mineral commodity supply cannot be taken for granted, right? And we've seen this. I started thinking about it a while ago, but definitely this year, but I actually think the pandemic was where things kicked off big time. Seeing the logistics delays, export controls, high cost uncertainty, and geopolitical disruptions impacting our supply chains. And in particular, what's been a big focus for us the last 2 years, really, starting especially in July 2023, with some export controls coming from China. This is sort of a timeline of some of the different export controls and the commodities that have been impacted by these export controls. And so starting in July 23, announcement of gallium germanium export controls, and going up until, even though in November 2025, the suspension and pause of export restrictions on rare earth elements, lithium ion battery materials, gallium, germanium, antimony, and super hard materials happened, there's still limitations to how those materials are allowed to be used. And so there is a desire by the Chinese government to track these mineral commodities so that they do not end up being used for defense for the United States. And this is an issue for us, right? Okay. So when the gallium export controls were announced, USGS we were looking at this and we were asked to do a quick analysis for the rest of the government to be like, hey, what does this mean? What's this used in? And how important is China? What exactly can they do, right? And well, the first thing that comes up is, well, they produce 98% of it. So yeah, this is a problem. And then, well, it's used in radio frequency. It's used in power. It's used in photonics, in LEDs, in solar PVs. And what this means is your cell phone, your defense radar and communication systems, your EVs, right? Your cars need it, and your electronic displays need it. So really, this is a huge problem for us, right? And we might not see the gallium being imported as gallium, but we absolutely know that it's there in our goods, in our products, in our technologies. And so, what we did was we started looking at this. Okay, what does the trade control look like? And we quickly realized that we could track some of it, right? So we have data on gallium metal imports for the US, but some of these trade codes that were being controlled were ones for which the data was being restricted and we did not have information. So we didn't even know how much gallium was coming in these other forms of gallium arsenide, gallium phosphide, gallium oxide, because that data was restricted, right? So this was an interesting project for us, and we started putting the numbers together to understand that. And so we started with what we knew, right? With imports and exports of wafers. What does it look like for wrought metal, unwrought metal? And where are the gaps? Can we put this together? So we quickly, can say, okay, we think China's producing about 628, and these are small quantities, right? 628 tons, I want to say, of gallium. I should have put the units. I work across the periodic table and I forget sometimes, but I'm pretty sure this is tons. Yes, of gallium in China. And outside of China, there's only about 10 tons being produced. I don't know if folks can track that. Right, so this is where I'm saying like the 98%, right, is being produced in China from the low purity level stuff. And large part of this is going into refined production. There's some recycling happening, and then it's going into semiconductor devices. That's one of the biggest uses of gallium. But it's also being used for permanent magnet manufacturing, which we're not showing here, but from magnets that goes into electric vehicles, that goes into your cell phone, motors. And then here, outside of China, there's, so China produces all the magnets, which is why you're seeing all the gallium that's being produced going into Chinese magnets, but we're importing the magnets. And then outside of China, there's semiconductor device manufacturing that's happening. That's where some of the gallium is going to. So that's sort of the quick and dirty material flow analysis. And so that's kind of traditional material flow analysis work that we do, tracking material balances across the world. What we wanted to now do is bring in some of the economists on our team to say, hey, what does this mean when there's a supply disruption to the price, to the supply availability outside of China? Are we incentivizing producers outside of China? when the prices go up. And so we looked at trying to estimate the elasticities for these for gallium and what this means for when the supply curve shifts due to a supply disruption relative to the demand curve. So we have a demand curve. We estimate our price elasticity. That tells us how steep this curve is. We have a supply curve before the disruption occurs. And that gives us sort of a price, a quantity for the global market for gallium before a disruption happens. And when we model what happens when China stops producing, we know how much China is producing, and we can shift our supply curve. And then we know outside of China how much people are producing, but we also know how much capacity is available outside of China. And so while the production is only 10, there's actually capacity that can be brought online pretty quickly. And so we can put that into our supply curve. And that gives us a new equilibrium point with a new price and a new quantity that's going to be reached, right? So this sort of gives you like an idea of where you're going to go. And this is, you're all probably thinking, at least when I started working on this is not what I was trained to do, right? I'm a metallurgical engineer, material scientist. But this is what needs to be brought into our analysis to understand how the materials that we are developing, how these new how the new supply that we're bringing online is going to be fed into the global market. And so, that gives you like this new equilibrium point. And what we also know is that the economic model, so in the short run after a disruption event, economic agents will attempt to retain their pre-disruption economic activity patterns as close as possible. So if you were using gallium before, you're going to try to substitute out a little bit, but you might not be able to do that quickly, and you're going to try to maintain it. And so we can use an economic model with an input-output table to understand the impact across the US economy of a gallium supply disruption. And so we want to minimize the change because that's what most of these economic agents will do. But there are now new constraints with a post-disruption material, commodity consumption, availability. There's a constraint on how much production can happen based on already installed capacity. And we have this new price that's going to impact the value added of our downstream industries that now have to pay more for the gallium that they want. What we were able to show is under like a very all of China export restriction kind of situation all of and up to like 10%, 20%. So a fraction of the restrictions is that like if you go to the full restriction, you could be looking at a GDP decline of over 3 billion, which is not huge, but it is an impact. And it's something that can tell us, hey, this is the size of your problem. If you're going to put policy in place to like address the problem, this is about the amount of money that maybe like you should be looking at. It also tells us sort of what are the industries that are most impacted, right? So like obviously this light blue, semiconductor and related device manufacturing, we know gallium is being used in the semiconductor industry. That's the first industry to be impacted when they can't get gallium. But downstream, right? So like obviously then you've got the printed circuit assembly, motor vehicles. Those depend so much on your semiconductors, right? Anyone who's stepped into a new car knows how much semiconductors goes into a new car. But also some other applications such as, other equipment, other electronic components, etc., appliances and electronic goods. So that's a base case range. But what's really nice about this model is that we can also look at different scenarios, right? It's important to realize that we're not predicting the future. We'll never be able to predict the future. If I could, I wouldn't be here. I'd probably be, sitting on an island. Well, except for the fact that my kids probably need to go to school. But, so let's look at what uncertainty do we have? What aren't we sure of? And let's run some scenarios to look at these alternative potential impacts that we could face with a gallium supply disruption. And so we looked at the very basic level, just like, hey, what if we were wrong with what we think China's net exports look like? Let's put a low impact, high impact case through, right? Let's look at variations of U.S. apparent consumption, excess capacity levels, and then run these three scenarios. And so we have that in our paper, but also right? We have now the model and the tool to answer these questions when other folks in government come to us and say like, hey, can you run this different scenario for us and let us understand what might be happening? And we can do that. So this brings us to so that was all work we did after the 2023 gallium supply disruption occurred. And then this year, we have gone through the whole periodic table of elements and tried to collect all the data possible and modeled 84 different mineral commodities to understand what makes a mineral commodity critical. And so the definition that the USGS follows for what makes a commodity critical is based on the Energy Act of 2020. This is something really important, I find, because criticality, it matters who you are when you ask that question. So if you are a producer of aluminum, aluminum should be critical for you, and so should bauxite and everything else that goes into that aluminum production. But for the US government, for the federal critical mineral list, the definition of criticality is a non-fuel mineral or mineral essential to the economic or national security of the US, which has a supply chain vulnerable to disruption. We also characterize critical minerals as serving an essential function in the manufacturing of a product, the absence of which would have significant consequences for the economy or national security. So I bolded a few of those words, and in particular, I also want to point out that this is for the US, right? So we have a very US focus on what is defined as critical for us. And so, this is available online if anyone's interested. We use that kind of same kind of model to build an assessment for all these commodities to understand criticality. And that model starts with a scenario quantification. What kind of supply disruption are we looking at? What is the response of the market when we have this supply disruption? So what's the price elasticity for supply and demand? And what's the available output that can increase domestically and in the world? How does this impact the US economy and all the different industries that the US economy entails and uses mineral commodities and depends on mineral commodities? And then what is the probability of a supply disruption? Like, how likely is it that we have a disruption from Canada versus China versus, Europe? So that's the scenario probability module. And we put it together, and that's what makes our, exposure, vulnerability, and hazard for our risk assessment for the Energy Act, for the critical minerals list. So we ran 1,200 different scenarios, and a subset we found had quite elevated risk. You can see here, like, for example, some of the rare earths, praseodymium coming from China, neodymium coming from China, tungsten coming from China, but also we saw high disruption levels from some of the precious platinum group metals like ruthenium, rhodium, and others. And this tells us sort of like, hey, okay, this gives you the sense of like how big could a disruption be for the US economy. And our scenarios were based on how much does the US import from each of these countries, how much capacity is available outside of these countries if this disruption occurs. And that made up like the 1,200 scenarios because we ran them all. And then our modeled impacts were then weighted by the probability of each scenario occurring. And that gives us the overall risk evaluation. And our findings were that, for example, samarium came up at top. That's a large impact. It is a mineral commodity that is a rare earth element. It is used almost solely for defense. But we also found like rhodium, high price inelasticity, is a very expensive material. It does not, people who use it want it, absolutely need it, and don't have a substitute for it. But this is the top 20. So you can see, in particular, right, an over-reliance on single producers, largely with China being the light blue of the impact. A lot of these rare earths, samarium, lutetium, terbium, dysprosium, gadolinium. I'm just now showing off that I know how to pronounce them. Yeah. And then what we found was, what we were able to do was like say like, hey, what is it that causes the U.S. economic impact, right? And what we're seeing is that the consuming industries for these mineral commodities are forced to reduce their output, or they're forced to pay higher prices, resulting in additional downstream impacts. And many of these scenarios, as you see, are tied to import reliance on China with few alternatives of other suppliers. And then once we had all the results, we're like, how do we group these? How do we understand, like, what are we looking at, right? We can just put them all in a line and say this is highest to lowest, but we can also try to group them. And this is another part of our having economics in our group. Benefit is, they built this Jenks natural brakes optimization method, and we grouped the commodities into negligible risk, limited risk, moderated risk, elevated risk, and then very high risk. And so this way you have like this kind of comparison across groups of commodities, and you can say like, okay, let's look at these first maybe. Let's have an understanding of why these are here. What is it that puts them there? And then maybe we come to these other ones later on, if we're trying to think about how to address the risks. We also found some having negative risk, and part of that was because when there is a supply disruption and the price goes up, if the U.S. is a producer of something, such as like mined copper or mined nickel, U.S. producers benefit because the prices go up. And they're profiting when this disruption happens. And so we also noticed negative risk. We weren't able to evaluate all the commodities quantitatively. We really just did not have data on cesium, rubidium, and scandium. But if anyone knows anything about these, definitely come and tell me about it. But we were able to, for example, know like, hey, we sort of know where they're produced and that we're very highly import reliant on them. And so in some cases, we recommended them still for being added to the list. And so that comes to like, what does the list contain? And so this is the Federal Register notice sort of printout. Our final list had 60 mineral commodities. But what I want you to take away is not what's on this list or not on this list, but that like we have created these tools and models that can enable a better understanding of risks and mitigation options. We have these supply elasticities to understand market dynamics for 74 non-fuel minerals. And we've tried to understand barriers for trade and how likely it is based on historical data for countries to impose trade barriers and what kinds of trade barriers have been imposed in the past. And we also have this optimization input-output model for the United States to assess different scenarios of supply disruption, right? And so this can be used with any kind of disruption coming forward, and we can build on it. And this is just part of our ongoing efforts, right? So we're updating and improving our data collection and assessment efforts to ensure that we work with the best available data. For the DARPA Open program, I've been working with a team to assess structural price and evaluate costs and incentives for building capacity domestically. And that data is being used by the US government right now to think about how do we incentivize domestic producers for these critical minerals. And we've been modeling the dynamics of supply and demand to prepare for potential future supply disruption in scenarios and communicating our analysis. I think this last bullet is particularly important. We do publish everything that we do at some point, right, after the whole journal review process. And that's like where you can find a lot of the information of what we've done. So there's more to come. And so I just want to end with saying that, like, really, we are taking a full supply chain approach, and I encourage everyone who works in this space to think about the full supply chain occasionally, even if it's not your PhD topic right away, right? And this means, right, so those of you in geosciences, you're starting with that exploration and mine development. You're thinking about what's your resource. Then you have to think about, okay, how does that resource become a reserve? How do you get that to become a mine that's commissioned? And how does that feed into the supply chain so that we have the mining concentration, processing, refinery capabilities to bring these mineral commodities into the market so that we can have our cell phones, our technology, our cars, our energy, energy sources going forward. And how does the US fit with the rest of the world, and how does trade fit in? So that's really where I want to end this talk, thinking about this full supply chain. Yeah, so that's kind of a mouthful of a last slide, but I thought that you could all handle it. That's it for me. Yeah.
Thank you, Elisa. Do we have any questions in the room here? Rudy?
Has the disruption from the tariff wars provided you a kind of natural experiment with seeing whether some of these ideas are bearing fruit or true?
My supervisor just asked me that question a few days ago. He's like, oh, do you think we'll have like data? So trade data does take like a few months to get published. But yeah, we're looking forward to seeing the data that comes out. Price data, though, is available. So we have started tracking that.
Elisa, in my class, I sometimes use the mineral commodity summaries, and the students have to look at it and say like a reflective essays type thing. Now, with what is happening for last, I would say 2-3 years, and you are catching up much faster than it used to be. So it used to be like 2 years late, 3 years late. Now we probably are, even 2025 is probably also out. So, but even with that, is that publication very, very useful in like a dynamically, or what's the latest source the students or somebody who is doing maybe research, for them it's even more important?
Yeah.
What's the best source for such information now?
Yeah, it depends on how detailed you want to go. But I do think that the mineral commodity summary, I use it all the time as the starting point, right? So like this gives me a quick sense. And to be honest, some of this information doesn't change as much as you'd think. Like you're not going to go from, I mean, some of it changes, but in most cases, right, US producers that produced last year will still be producing this year. The amount that we were importing last year is probably similar to the amount that we're importing this year. So a lot of that data doesn't change as much as it's not, for a student level, that's not an important, I think, aspect of these markets. If you do want more data, I think you have to wait for our yearbooks, which are unfortunately more behind. And then we actually just have to go through and pull in census data, Bureau of Economic Analysis data. Like we just have to pull in our own data and do our own analysis internally. But I think for students, that's probably a really good place to start.
I'm interested in the case of aluminum. I mean, so many of these are rare, minerals, but aluminum is so common. So what can you just talk through the story of aluminum and what makes it a critical mineral? And
yeah, well, we import 100% of the bauxite so our metallurgical bauxite is 100% imported. We do have a number of sources for our bauxite. We have only one alumina refinery domestically, and so single point of failure is one of our considerations. And so while we refine aluminum, upstream to that aluminum, the feedstock that's going into those refineries is all imported. And so the way the model works is that if at any point in the supply chain we identify a critical supply chain risk, then that commodity goes into the list. So that's the short story. I'm happy to go into more detail, but do you want more detail? So in this model, we're not using a defense approach. Like we're not thinking about the enemy, friend kind of situation. What we did do was looking at just like which countries have imposed trade barriers on us historically, and how does that like play a role for the probabilities of a disruption. So that's, in the previous cycle, the 2022 list, we had data that told us like what the willingness to supply from each country was. So that was like a slightly different approach to it. We do like changing up our method so that we improve it every 3 years. We'll see how this method goes, but both of those are ways to think about where you're getting material. But like I said, like having just a single producer of like single refiner for alumina and being 100% import reliant for bauxite are more than enough to put you on that list.
Along those same lines, I was curious if any of the scenarios include natural hazards also as sort of perturbation.
Yeah. So natural hazards, I think, yeah, so here, like for example here, earthquake disruption. So we're trying to build that capability, right? So we did have this, like that was a collaboration with the earthquake folks at USGS. And so Chile lies on a fault, right? So yeah, we would love to increase that capability to think about disruption from natural hazards. One of the things that happens with natural hazards is usually we actually bounce back quite quickly. And so the disruption level won't be as strong as a trade barrier, just like won't be as long lasting usually as a trade barrier disruption.
Thanks. So I'm gonna try to set aside my opinions on this question and ask with curiosity. Um, for growing emphasis on things like crypto and AI, where we have increasing demand for new data centers that require materials, set aside the water and energy, but just the raw materials for the semiconductors and whatnot that go into building these, are those considered as factors in national economic security and defense, and kind of how do we account for the accommodation of that growth, I guess, is one side of it. And then the other side is, are there internal competitions within the United States for these same commodities where one use may be pulling resources away from another?
Yeah, so we are doing our best to try to improve our growth kind of forecasting capability, right? So again, I cannot predict the future, but to understand potential scenarios for growth is definitely something that in this space, a lot of analysis is being done, and the AI space is one of those. I think the price elasticity does something to track like that competition, right? So if you're willing to pay more for a commodity, you know, if you are an AI farm and you are willing to pay more for gallium than the electric vehicle folks, well, you're probably going to get it and they might need to substitute out. So that's sort of like, that's just basic economic, right? So like then the question is, can you quantify it? Can you sort of show it? If you know, and then from our perspective, it's just like, can we quantify it and understand it? And then probably like if you were a car company, you better understand that, because then you may have to pay more if you're right. So that's then becomes a much more detailed question.
I was just going to follow up on the environmental risk question there, because, you know, there's a natural hazards thing, but there are things like sea level rise, climate change related flooding risks, and this kind of thing, that kind of progressive strains on the system, not just a punch in the gut, but just a, you know, tightening squeeze. And it seemed like it'd be helpful to build those kind of risks into the model as well.
Yeah, so any of these, especially in these minor metals where there's really just a few producers and facilities globally outside of China. China usually has a few more of them, but outside of China, you're talking about just a few. Then any kind of disruption is potentially really bad. You're not talking about, like, I mean, copper, for example, there's 300-400 producers, then that's not, you can't imagine it hitting them all at once. But for something like platinum group metals, when something happens in South Africa, you're hitting a lot of it.
There's kind of that immediate risk from an event, but then there's just long-term, you know, continual strain on those supply chains as well. And it's geographically distributed.
Yep, for sure.
Yeah.
Thank you for that talk. It's very interesting. As a fellow materials scientist who's looking at critical minerals, I know a lot of work is being done on trying to increase extraction efficiencies, so reduce some of the externalities from mining, make things able to be produced on a shorter timescale using fewer like resources.
Yeah.
So is that sort of thing applicable to your models at all, or are they such a slow kind of grind towards progress that it's not applied at all?
Yeah, no, absolutely. And I didn't even show some of our supply curves, but you're right. Like, so as part of the DARPA program, we're trying to really understand like the cost basis for these, for the production and refining of commodities. And in some cases, the reagent, for example, or the energy cost, like you'll see one of their OpEx, operational cost, huge part of that operational cost will be, let's say, energy for aluminum or magnesium, right? It'll be a reagent for the rare earths or for the, definitely for the rare earths. That's the one that's coming to mind. Gallium, actually, it's also one of them. And so if that cost can come down, if you target your research, if you understand the big picture of the costs and you target your research towards the biggest bulk of the cost, we can definitely make a huge impact. And the question is when and how fast, right? But that's the same question, right? Just the question is just how fast can you do it?
You're doing this amazing job of identifying threats to our national and economic security. And I was just wondering how this work by the USGS is getting communicated up the administrative chain to inform decisions about tariffs and the like. Is there a mechanism by which the USGS is able to communicate to, the executive branch why tariffs are maybe not in the best interest of the United States?
Well, so that has a bias, your question, but I will say that, well, so, we publish everything that we do. So but that takes time. When we get asked, the other thing is we are part of the executive branch, right? So USGS is part of the executive branch. We're not part of the legislative branch, and definitely not the judicial. But we answer the phone, right? I get an email, and if someone's asking me a question about a commodity, I answer it. And that's, the person obviously had to have an interest and want to ask the question, but that's one way that questions happen. Of course, if someone at a higher level asks the question, then it gets trickled down to me at some point. But but that's usually how it works, and we do our best to answer as quickly as possible. Any question that comes our way, if needed, we'll say, hey, get on a phone call. Let me make sure I understand the question right, and then answer it, right? So sometimes the questions are a little, general maybe, for example, and then I'll be like, hey, what is the specific question? Let's get on the phone. That's where like getting on the phone makes the most sense, right? What is your role? What is it that you're really trying to figure out? And then I try to answer it.
Okay, that's great. But, I'm thinking about Sue's question regarding aluminum.
Yeah.
I'm a mineralogist. I had no idea that we were importing all of our bauxite because we have massive bauxite deposits domestically. And so I don't know who is actually providing our bauxite, but it's pretty scary to me to learn that all of our bauxite is coming from outside the US. That's something that I would think would be communicated to pretty high levels in the government as a national security threat. Is there a mechanism for that?
It's in our commodity summary. So that's for sure. It's on we have a bauxite mineral commodity summary. There are two forms of bauxite that are like really usually right on the market, right? There's the metallurgical bauxite, which is used for aluminum, and then the refractory bauxite. And I'm saying this off the top of my head, so if I'm wrong, I think that's right? And so I think the domestic production is mostly refractory and it's tiny, or it's 100, I think, sorry, I should say. If I'm remembering correctly, 100% of our domestic bauxite production is the refractory form, and it's not a lot of it. So then the question is why, right? So the question why, then I would have to spend a little more time. I haven't looked at it recently. Probably our aluminum specialist might know, but my guess is it's not cost effective. Usually that's the bottom line. I think Jamaica and Guinea are like where we're getting it from, right? Yeah.
Okay to ask the second question.
Yeah, of course. I mean, at least I don't mind, but the refineries, that's correct. The refineries are closing domestically, and it's been an issue because the energy costs domestically are not. So the refineries for aluminum and alumina tend to be located like in Quebec, Norway, Iceland, I don't know, but I do know Norway and Quebec have it. And then, I mean, upstate New York has had one. And then, but then also like Qatar, so they're using it as a byproduct of natural gas that they produce. They can just have the aluminum refinery there. But that's the refinery part, not the bauxite part. I think the bauxite is just a matter of digging it. Go ahead.
It's like soil, yeah, bauxite
Right? It's
is
like
like,
easy
yeah.
to, yeah. Again, I've never been to one of these places, but I try to track the whole periodic table of elements. So don't ask me too much detail about any one.
I'm just
For merits.
piggybacking on Dinkam's question about the other factors involved. I know that USGS, your mission is to like say science and technology wise and not so much on the human side of it. You probably know that yesterday they killed about 70, 80 people in Congo. So it was, yeah.
Accident.
So
Yeah.
before cobalt becomes such a heavily demanded commodity, they're killing people with other things. Now they're killing people during mining. Like what happened, like say the army opened fire, people started running, stampede. Now in one of those risk analysis and any human factor are being considered, like it's not probably in your territory to like, oh, I have to change the regime and have a benevolent government or something, but any of those risks are considered in your models.
Yeah, so we have looked at like risk from like a governance perspective, and that's a factor, right? So I'm not visiting any of these locations, but we can take other anything that's so what's, for example, the CIA or what any other agency would have put together as risk factors for governance and use them in our analysis for understanding supply risk disruption. It wasn't used in this version, but that's absolutely something that can be done.
All right. Is there any questions online? I don't see any in the chat except for Dave's, but I want to give people a chance to unmute and ask their question if they want to. And if not, I'll ask Dave's question. All right. This is from David Russ. He's asking, is knowledge of impact of supply disruption accelerating U.S. efforts to increase critical minerals processing within the U.S.?
I think, well, so there is definitely increasing knowledge of supply disruptions, and there's definitely increase in processing capability investment. The correlation versus causation between those two, I'd love to say that it's increasing knowledge is leading to increasing investment, but I haven't done the analysis to know if one is leading to the other.
Okay, thank you. All right, we can give Elisa one more round of applause. Thank you. And the recording of this seminar will be posted to EZ's YouTube channel. And if anybody needs the link, reach out to me and I can get it for you.
Thank you.